I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism podcast, an exploration of the past, present, and future of material science. My name is Taylor Sparks, and I am a professor of material science and engineering at the University of Utah. But I am not at the University of Utah. I am here at the University of Washington with my friend Eleftheria Roumeli. Eleftheria, thanks for inviting me out. I'm here for a seminar, and it's been a delight to meet you guys and meet your campus. How are you?
Great. Thank you for visiting us. And it was a pleasure for everybody to have met you in person.
Coolest thing, we had one of the students in the audience who said that his girlfriend is a fan of the podcast, and she had given him a copy of her Intro to Material Science book for me to sign. That's never happened. That was the coolest thing ever.
People were excited to see you here. I was not exaggerating.
That was so cool.
Go.
Well, Eleftheria, tell me about yourself. Who are you? What's your background?
Okay. I'm an assistant professor in the University of Washington in the Material Science and Engineering department, so same as you, I guess. I'm a physicist by training, so I have my undergraduate, master's, and PhD from the Aristotle University in Thessaloniki, Greece, where I'm from. And then I took a 5-year postdoc detour before starting here, where I spent a couple of years at ETH Zurich, studying.
Oh man, so nice.
Yes, in the mechanical engineering department there, and then 3 years at Caltech, also in the mechanical engineering department.
So
before
physics undergrad,
here.
Mechie, and now materials.
Physics all the way through PhD, 5 years of postdoc in Mechie.
I see.
So,
wow, you've done a lot of stuff.
Yeah.
And now 5-6 years here at Washington?
Yes, it's my 6th year here in the Material Science and Engineering department, where I'm a professor here, but I have never been in a material science department before, which is kind of funny, I guess.
You're an honorary member of the club. We're so glad to have you. So today, you reached out to me at a spring MRS meeting saying, hey, let's talk more about biodegradable plastics, which I am always delighted to do because it's a huge world. And even though we've done a couple episodes, in fact, if you check back, listeners might remember episode 86, I think it was, on PHAs. They'll remember we've talked a little bit about this, but there's so much more. So today, I thought that we'd get a bit of an overview of this idea of sustainable polymers, bioderived, biodegradable. I'm using words interchangeably that are not interchangeable, but let's introduce a little bit of that and then talk about what you do and then talk about what else is out there, okay? So to get started, there's a really great review article that everyone should go read. It's in Annual Reviews of Materials, great journal. Eleftheria and her team wrote it. And they talk about, broadly speaking, some sustainable polymers. And I love your first introduction. You're like, well, we can break this into sort of 3 categories. You've got biomatter, so fungus, algae, wood, whatever, right? Biosources.
Means biological matter.
Okay.
A term introduced by my postdoc, my first postdoc, Andrew, when we had a brainstorming session that was never ending, and we had to come with a new word because we didn't want to use biopolymers. They have been associated with biomedical
applications. Yeah, it means something very specific, right? So this is a broader one, just biomatter.
It means biological materials in general. Okay. So my American postdoc, Andrew, who loves conjugating things, he came up with it. So now other people are using it in their papers.
Nice.
And if he's, you have him to blame, I guess.
Well, okay, so we're going to start with biomatter. And then you can do sort of 3 things with that from a sort of materials engineering perspective. You can break it all the way down to monomers, right? And then you could use the monomers like you'd use them had they come from oil or wherever else, right? Your second pathway is you can use the polymers that are naturally produced by that bio species or whatever, right? Example would be like wood makes starch. I'm getting that wrong, right?
Or silk from spiders.
Or silk from spiders, right? So some sort of biological process produces a polymer, and you could use that polymer without breaking it down to monomers. And then the last one is don't even break it down to like the polymer. Use it in its macro scale, like in its macroscopic dimension. So when mushrooms make the funky shape that mushrooms make, you could use that funky shape. Am I getting this right?
That is exactly right, yes.
Okay. So
that's the way that we actually kind of think about it. Other people present it other ways, but this is, I think,
but I like this
nice
breakdown. It's hierarchical,
yeah.
right? It scales.
Yeah, exactly. It is hierarchical because we want to stress that it's not just the chemical components that you can get. It is also this hierarchical arrangement that nature has I guess, spend so much energy to create from the bottom up.
Yeah, and
we should take advantage of that.
Maybe you don't want to undo it to go all the way back to monomers if you could use that structure that it's already created, right?
Because pretty frequently, if not at all times, that structure always has a higher, it has an added effect. So you have whatever strength is from each of individual component, but then you add on it whatever comes out of the way that they are arranged in 3 dimensions, right? And hierarchical structures made from natural organisms typically are the definition of multi-scale materials, which we cannot make in the lab. If you were to synthesize now something in the lab,
how do you do that?
That has periodicity in the nanoscale all the way to the meter scale.
Yeah.
You can, I mean, it will take you a few years. You can do it, but it will take you a few years.
And nature just does it for us. It grows like a weed.
Room temperature, like relatively mild pressures.
Yeah, no furnaces. Super, super cool. So of these 3 areas, where do you see the most research happening right now? And what part of it is most aligned with what your group does?
Sustainable polymers in general is basically a new thrust within traditional polymer science, right? So because people have spent 100 years optimizing how we synthesize polymers, it's only natural that the majority of efforts regarding the sustainability initiatives that we care for now are actually synthetic. How do we depolymerize? We have beautiful catalysts to make our polyethylene. Let's find other catalysts, or the same ones if possible, to break it down to monomers. So majority of people actually are working on that chemical depolymerization processes for recycling or for degradability, I guess.
So when people talk about upcycling, for example, that would fall in that category. You are doing a chemical treatment to transform it to some useful state at the end of its life, for example,
or make something useful out of an intermediate. There is beautiful, really significant push and beautiful works in that domain. And that, I have to say, is the majority. If you really want to talk about sustainable polymers, I think majority of the field actually is focusing on that. Now, there is a smaller part of the field that is focusing on utilization of biopolymers or having organisms do the synthesis for you, which is closer to what we do.
Yeah, we saw some of that in your lab today. Yeah. Super cool stuff. Tell us about it.
And in our approach, I guess the difference is that we want to use all the organic components, all the polymeric components that organisms have generated for us. So we take a lot of, we have a wide variety of organisms that are of interest, primarily photosynthetic ones. So we really care for seaweeds or microalgae or other photosynthetic species, if we can focus on those, just because for their growth and their ability to synthesize the biomass, they actually consume CO2. So if you do the calculation afterwards for how much CO2 you consumed in the process, you really want to, if you can, start from something that is photosynthetic, you should. So that our approach is to start, if we can, from photosynthetic feedstock.
Yeah, because you're not only not emitting CO2 via energy use, furnace use, or whatever, but it is a sink of carbon dioxide in the atmosphere as it grew in the first place.
Yeah.
Okay.
Of course, not infinite, and you have to do the real work to find out how much of this you can actually save and how fast the organism reproduces and all of those things.
Rates.
But at least when you start from something like this, or if you start from something that is waste. So we also, I didn't show you, but we also have coffee waste that is from the cafeteria. We have food waste that is from like our own, can be from our own sources.
And again, most of the time they'll try and put that in a bioreactor to get it all the way back to methane or something. But you're saying maybe in its current form there are uses for it as as a filler? Like, is this primarily as fillers, or are there non-filler, like actual functional applications of these polymers?
We actually go for bulks. Like, we want to see how we can use biopolymers as they come from natural feeds, from organisms, as actual polymer matrices. So we want to use them as an alternative polymer, not as a filler. I mean, you could, and we have a paper that we just use them as a filler for PLA. We have some other things that you can put them in polyethylene,
concrete,
polypropylene.
you can add a little bit without degrading things.
Exactly.
But you're saying in and of itself, it can have value.
Exactly.
So somebody who's listening might be like, okay, how's this different than what humans kind of always done? Haven't we always taken natural fibers and turned them into engineering, which are like turn hemp into rope and things like that? How is this different?
We have, actually. And we have, for thousands and thousands of years, we know how to beat wood to make it into pulp so that we can make paper and write on it. Absolutely. The new thing that we are proposing here is let's not spend the energy to break down every component, even if it is to keep the polymer. So for paper, you use cellulose. So you keep the molecular weight that is made from wood, from a tree, I guess, or from a plant, but you remove everything else because that's the only thing that you need, right?
I see.
So we are looking at it as a composite, basically. And if you think about it as a bucket of your Legos, I think that's the best analogy for people to understand it, actually. You have a bucket that has already generated thousands of Lego pieces. We just find ways to A, identify what they are, B, change the way that they are arranged. So that you can actually, you said it in your talk today, actually, you can have, 10 building blocks, you can make thousands of, or infinite, actually, combinations, right? It's the same thing here. So you have let's think about our simplest example is actually the spirulina plastic that I showed you in the lab. So this is a very, very simple.
Tell us what spirulina is if people aren't familiar with that.
Yeah, so that's a cyanobacterium. Sometimes people call it also a blue-green algae. It's a photosynthetic unicellular organism. So it's a single cell.
I've been eating this stuff. I did not know what it was.
Yes, you eat it
algae?
because it's a...
No, my wife puts this in our smoothies and she loves it. So what's it? All right. So it's a type of plant.
It's a type of bacterium.
A bacterium. Okay.
Cyano means blue.
Okay.
Greek.
Okay.
But anyways, this is a high protein feedstock. It's a single cell organism. So if you keep feeding it, and we had it in the lab, we used to culture it, but you now have ponds of it. People grow it for food, but also for fuels and chemicals. It's a single organism. So if you keep growing it or feeding it, it will divide, but it will never make like leaves and roots.
It's small.
A single cell.
The cells are a couple microns. A couple 3 microns. So this is not going to be a macro thing.
No. It actually assembles itself in chains with mother and daughter cells, but it doesn't form like a tissue or a 3D structure or a leaf or nothing like that. So it's a single organism.
And there's uses for it in its cellular form, you're saying?
Exactly. So the way that the reason people think sometimes in our field that spirulina is the only organism that we use in the lab, which is not true. It's just that it's the one that we kind of present the most just because it's the simplest one and it's a little easier to explain. So you have a single cell, you have 55 to 65% protein.
Okay.
These are different types of proteins from 15 to 70 kilodalton. So it's not just one type of protein. Yeah. You have a very thin cell wall, 20 nanometers, where it's a relatively thin cell wall, so you can break it if you want to just crack open the cell. You have about 15% carbohydrates, but not cellulose, nothing as strong and stiff.
Yeah, this is not a strong structural material
but
typically.
Still, you do have carbohydrates that are relatively high molecular weight, so you can still have like a structural fiber there, if you will.
I see.
Protein to connect everything. You have a little bit of fat, about 10% fats. You have some aromatics as well, which give other properties. So this is the simplest, I guess, life form that we have in the lab that we started analyzing and started to learn how can we use heat, pressure, or maybe changes in pH, because those change how proteins arrange, right? And how these components are going to interact with themselves. How can we make sure that we react them in a way that gives us, at the end of the day, something that has properties that are useful?
Dude, you're kind of blowing my mind because I saw these parts in the lab today, and we're going to show some cool pictures. If you check out our Instagram page, like I'm holding one right now, I would have thought this is made of wood or like a high plastic, right? This looks like polyethylene. This looks like Delrin. This looks like a regular material. That you're telling me this came from plants wouldn't surprise me, but single organisms without that extended macroscopic structure is very surprising. So how does tiny little cells turn into this, what looks like a engineering plastic?
So for us to make this into a bulk material like this, it does require processing with specific temperature and pressure. So we use either a hot press or an extruder. For this, we did use the hot press. Actually, surprisingly, the temperatures and pressures are quite similar to what you would process. I did my PhD in polyethylene. So
and it's
actually,
not so different?
It's not different. It's like 120 degrees Celsius.
They always say that people are like 70% water or whatever. Is that not the same with these things? Are they not mostly water? Is there like a major dehydration step first?
You're absolutely right in that What we used here is the same powder that you use to beef up.
That same stuff.
That is
so
exactly
it's been
what we
dehydrated, freeze
have.
dried, or whatever.
Yes, you can sun dry, air dry, freeze dry. Of course, that is a very high energy. So actually, that's the hot spot.
I see.
That typically, if you actually use a freeze dryer, that's what will kill your life cycle assessment calculation
that's
afterwards.
Not the way to do it. So but you guys tried other ways?
So we actually get it dry. The one that we grow in the lab, you can air dry it, but for none of those, we were not using ours. We actually used the commercial one for those because we needed a significant amount. And what we grow in the lab is like, a gram at a time. But we also do the same for seaweed. So after we saw that thermomechanical processing allows us to basically change the conformation of proteins so that they create a cohesive matrix around the carbohydrates that are like a structural fiber.
I see.
And your small molecules, we don't exactly know their role yet, but we think that some of them are functioning as plasticizers, so viscosity modifiers, and some are functioning as defects. The lipids, for example, they would self-assemble and phase separate. But when we saw that this was happening in 2 or 3 types of biomasses, then we started looking also in seaweeds, which is a larger scale, a macroalgae.
And now you have a macroscopic scale to it.
Exactly. And not surprisingly, those are much, much stronger and stiffer. But the same principle applies, just in different reaction conditions. So you would need different pressures and temperatures for those.
So help people understand what you're actually doing, because I saw this in your lab today and it was wild. You've got some undergrads and they're just cranking away, just turning biomatter into polymers, right? And it looked to me like ceramic processing. They were taking powders, loading them into dyes, putting it in a uniaxial press. I think it was a heated one. Yeah. So it's a heated hot press, uniaxial, and out comes what I would have called like a green ceramic if you hadn't told me that it was food particles. But you're saying that it's different than a ceramic, which has very, very low green strength, because this has significant green strength. Yeah. I saw you put some screws in these things. Like these are, they're not like, it's not like you just took like flour and sort of compacted it. This is something else happening here because there's a change in the proteins and the carbohydrates where there's bonds forming and it's forming is it a network polymer? What's happening?
So there are both secondary bonds, so hydrogen bonds being...
Is it primarily secondary bonds, you think?
It is primarily, yes. We have the MD simulations that show that it's primarily hydrogen bonds, but there are also some covalent bond changes, which we're looking on right now. We don't exactly know if, to what extent the covalent bond changes are the ones that... I don't think they are the ones that are driving the reaction, but they are important. And what we do actually is we do a recycling study, not for demonstrating recycling because everybody mechanical because everybody loves it. So we have a coffee grinder in the lab where we put this afterwards.
That's so cool.
The first beam, we coffee grind it, and then we press it again and we test it in the test frame, mechanical testing. Then we regrind and do mechanical testing over and over again, 5-6 times.
Okay.
So that we can see how the properties change. Even if you do that with polyethylene, you will have, as you pass the material with either in the hot press or in the extruder, you will have some change.
It must degrade, right? It degrades over time.
Yeah, even for virgin polymers.
And your stuff, does it also degrade?
It also loses about 20-25% of strength in the second time, and then it is stabilized. It's still about this one, which is the weakest biomass that we have. Spirulina is the weakest plastic that we ever made.
Good. That's still pretty. Like there are many applications for this.
You can drive a car over it. It has a compressive strength of 70 megapascal.
Yeah, like there's applications for this, and you didn't have to take it all the way down to monomers. You used it in the form nature gave it to you.
Yeah, and it is absolutely not the strongest stiffest that we can do. It's very brittle though. Absolutely, it's very brittle. So we are working. As you said, the students that are cracking up samples, these are working for an NSF collaborative project that we have at the MREF.
Oh, cool.
In which we have to, it's a design project, right? So we have to understand what are the design rules, what is the role of each of those macromolecular components of all lipids, of all proteins, of all carbohydrates, so that afterwards we can really do design and we can say, I need to replace polystyrene. I need this tensile strength, this whatever modulus, so that we can tell you, okay, you need a 32% protein, a 25% carbohydrate, and so on. Ideally, without the element of location, because it's very, very important that we the whole vision that my lab, I guess, is putting together is local biomanufacturing. So you shouldn't have to import, or you should use whatever is here available to you. And ideally, you should fabricate it here using local resources and also have the end of life here. So these end of life is also an important part of our studies. Back to the recycling, I guess, studies that I told you about with the coffee grinder. The reason why we do this, we do these reprocessing basically cycles, and then we go with
that's not just like to figure out if you can use it again, right? It's beyond that.
I mean, okay. To satisfy the reviewer that actually wanted to...
Oh, that's what the reviewer too. Thank you.
So somebody wanted to see the recycling. So there you go. Yes, you can repress.
But while you're at it...
But while we're at it, we wanted to learn something about this. Because if you actually go in with spectroscopic analysis like XPS and FTIR or Raman...
And these tell you basically bonds. You can see the bonds that are present.
You can measure... It's a semi-quantitative we're measuring, but you can definitely see what kind of bonding you have in your material. So if we actually see every time that we process it, how much of the bonding motifs, how many of the bonding motifs change, secondary or primary, that will let us know exactly what are the changes that are happening. We actually are investigating that right now. We don't know exactly, even in our best studied system, we don't know exactly
so there's
which
change,
bonds.
But you're not exactly sure what and how.
Exactly.
Yet.
We have MD simulations from a collaborator of ours, Kayla Sprenger at CU Boulder, that in a model system, so we have now another approach in which we take cellulose as a proxy for carbohydrates, BSA as a proxy for proteins. It's the fruit fly of all protein studies. Two types of small molecules, a fatty acid and a small sugar, in ratios that mimic what we have in biomass, and we subject them to similar heat and pressure conditions, so that we can basically, in this clean system with only 4 components, we can try and learn something more than the messy situation that we have in the real case, because it's so difficult to, with the thousands of components here, different types of proteins, different types of carbohydrates, everything blended together. If you study the FTIR of that, it will give you a headache because you cannot really see changes. You cannot see if you do a DSC, there is no glass transition temperature. You have 3,000 stuff here. So then we have a clean control study with in which we are simulating, at least in chemical similarity, the composition here in terms of ratio, how much overall carbohydrate, how much overall protein. And we have one proxy for each one of those. We subject them to the same heat and pressure conditions, more or less. And then we study also the mechanical properties, bond analysis, and all of those, so that we can learn, basically, at least from the chemical composition, so hierarchical structure aside, what are the changes that we are inducing with heat and pressure. So the molecular dynamics that Kayla is doing are super important here, because they showed us how protein, even though we studied BSA, and it's not BSA that we have here in the real biomass, but it does show us this aggregation process that is the loss of secondary structure of protein. That is such a terrible thing for biological applications, but such a great thing for us, because that is why we have, we think, we'll see, because it's actually reviewing stage 3. So we'll see if
by the time this episode comes out, I hope that it's gone through.
Yeah. But this is the changes in the protein conformation, for example, in secondary structure, primarily, that bond the whole thing together. And then it's not a surprise that when you have seaweed, for example, feedstocks, where you have really high molecular weight, carbohydrates, or even cellulose, and low amount of protein, because it's just a binder, we think. That is why we think we see higher strength and stiffness materials, same process, but just changing the feedstock from micro to macro.
So I have a niece who loves to brew kombucha, and I never knew what kombucha was. I would just drink it, and it tastes like vinegar, but whatever. She loves it. And then I saw how they grow it, and it is gross, because at the top of the pitcher, there is this big, I think she called it a Scooby or a Scoby or something. And then I was like, what is that? And she's like, it's the bacterial mat or something. And you have this growing in your lab at like scale. You've got like a fish tank with like a big old fat like kombucha film. And what is it? It's a source of cellulose. So tell me what you're using that for.
Yeah. So I'm surprised that you found this gross because it's actually a very elegant biosynthesis system.
I'm sure it's wonderful.
I mean, it is
all my
gross
kombucha fans are like, cancel him.
Well, I do have some tasting studies that my students are doing every now and then.
And
maybe
they're amazing, I'm sure.
In the wild type bacteria, okay. So in the one that is food safe, not on anything genetically modified.
Of course.
I do have a collaborator that actually has eaten some of our bioplastics, I should say. I mean, she knows who she is, so I'm not going to say anything. But we had a collaboration. Every time she came in the lab, she tasted the plastics that we made. They were from strawberry or from coffee or whatnot. So even though it's not marked for food consumption.
Sure. So your cellulose, what are you doing with it?
Yes. So cellulose that comes from bacteria is slightly different than what we get actually from woody biomass. Chemically, it's exactly the same. So the monomer is glucose. It is bonded by the 1.4 bond or whatever it makes. So it's the same. But how the crystal is formed is slightly different, and it has much higher aspect ratio. So you can make very, very long 5 millimeter.
I thought you were going to say it's something about the lignin and the other stuff present, but you're saying the cellulose itself is different.
Exactly. So because people, I think they don't realize... it's not chemically, it is the same, but because the fiber is much higher aspect ratio, it is a distinct, I guess, difference between the two. But of course, the biggest difference, you're absolutely right, is that when you grow it from bacteria, it's the only product, and you don't have to remove other components. Whereas when we get cellulose from wood,
there's all these treatments to separate, right?
Yeah. Absolutely.
So this is a classic example, like why take it from wood where you have to spend the additional resources, energy, whatever it is, to get to the cellulose if, in this case, you could have just used it from a different starting source, which delivered you the cellulose? No?
Yeah. Yes and no. I guess, yes, in terms of this is a single product. So yes, you will not have to remove anything, but it is, because of the different aspect ratio, it's so hard to get it into an isolated fiber. To disentangle it. For us, we use it actually entangled, so it's pretty nice that it comes as a spaghetti mess. But for other people, when you have to isolate one, you do need to do chemical processing to beat it out and to remove, to break basically the hydrogen bonds that associate the fibers together. And people that work in woody biomass would be very upset if I didn't say that, of course, the scalability is uncomparable. Yes, we do drink kombucha and we do have bioreactors. All your beer, if you convert all your beer brewing business and beverages, you can produce significant amounts of cellulose that way, but I don't know.
It's like orders of magnitude different from wood,
I actually have not seen calculations that I really trust, to be honest, on that. So I couldn't comment on the scalability.
Now, the stuff that you produce, you have this great...
But it is faster growing.
I believe that.
Much faster.
I believe that.
We grow, the thing that you saw, that was about a centimeter thick.
How long that takes?
It's a week or 10 days to grow.
Yeah, it's not like a tree that takes years and years and years.
Yeah,
so you had this great review article. Loved it, by the way. Annual Reviews of Materials, great journal. My former PhD advisor is the editor there. Great place. One of the things you talked about in cellulose there, which I thought was, first of all, I didn't know cellulose was. I'm not an organic chemist, so I'm just like, I'd heard of it, but I didn't know so it's cool. It's like glucose that you've like chained together with like, what, ketones or what is that group? I don't know, like the oxygen in the middle.
Yes.
Very cool. And it was fascinating to learn how different it was as a function of the diameter of these things, right? The fibers that these can form, wildly different properties as a function of the thickness of that diameter and how they're aligned. So I'm curious, in the stuff that you're growing, how much of your effort has to go into changing diameter, aligning things, or does nature give it to you in the form that you're interested in?
So we have actually, maybe I didn't actually answer your first question, which is why we even grow this in the lab. We grow it for two different reasons. One is because it's a great model system for us to understand the fundamental polymer physics that govern the bioplastics, I guess. So it's a beautiful proxy for carbohydrates that we can control aspect ratios and surface chemistries also if we needed to. So we grow it for the fundamental studies. We study how it behaves in a colloid and how can you process it into foams. I think I showed you the styrofoam kind of equivalent.
Yep.
But so one is for our understanding that we grow it, but another is for the materials that we can make. So for us, we have some part of the group that is actually isolating and beating it down so that we can have this nanofiber that then we can load drugs on, collaborators of ours actually do these studies. They are real applications.
Okay.
Or we can use it as a fiber reinforcement in other things. But we actually do have a couple of papers out in using it in the mesh entangled form as a sheet, which you can
as like
control.
a paper, basically.
Yes, very expensive, completely unreasonable
Sure.
for you to use it as a paper.
Yeah, but maybe for some application.
But it has like exceptional properties, much higher
Yeah.
than regular
Yeah.
paper. Other people have aligned it into fibers.
Yeah, in your paper, you have this cool thing. It's called hydrodynamic alignment, right? So you have a mess of unaligned cellulose. And if you have these sort of, I'm sure that's like size dependent channels where you have some viscosity fluid flowing through, I don't know if it's just water or what.
With different salts.
With different salts, it helps align these things. Just like if I've seen studies of microfluidics, right? Where it aligns things. You're doing the same thing here to get fiber alignment basically out of these cellular fibers.
Yes, other people were, which I think
This is not you guys?
Not us. I think it's beautiful work. That's why we featured it in the paper.
Yeah.
And I think it still holds the record for probably the highest strength fiber.
Yeah, crazy. I was looking at these numbers.
Yeah.
Let me put up here. Like, look at this. 1,200 megapascals, 70 gigapascal modulus. That's wild. These are like, it's not what you think of when you think of biomatter. It's not, this is like engineering in metals, ceramics in some cases. And yeah, it's not toxic. It's not going to kill you. So,
but you know what? So this is a component. In that form, they were using plant-derived cellulose, and they were removing all the amorphous domains. So you remove all the disordered domains, and you keep this crystalline structure. It's actually a beautiful crystal also, either triclinic or monoclinic.
it crystallizes?
Yes.
Of course.
Then each of those fibers that you see over here is just the crystal, the nanocrystal. So it's about, I don't know, 5 nanometers maybe in length, what they used here. You can have different sizes.
Yeah.
And then you can flow different things with other salts so that you can also control the the hydro.
Oh, I see.
So you
you get the steric and the charge interactions.
Complexation, and you have the flow fields to align. So basically here they're using really nice processing technologies that we have already developed for other materials, but in this biopolymer system. But what I wanted to say for the strength of this material, and people don't really realize, I guess, this fiber is actually, if you think about carbon fiber, maybe epoxy that you think about, when you think about composites, I don't know, maybe in a material science program, when we say composites, the first thing that comes to their mind is carbon fiber with epoxy, I guess. Maybe it's because we're close to Boeing. I don't know.
Yeah.
But what is the function of so carbon fiber is going to be very high strength, very high stiffness, great. You need a compliant matrix. You put the fiber there to reinforce. That's the same thing that we see actually for cellulose, that is the structural fiber that reinforces plant cell walls. So if you look at the cross section,
it's playing the same role, yeah.
It's
aligned in the same way that we've sort of nature knew all along. Nature knew all along.
Exactly.
That's so cool.
And if you see the successive layers of cell walls in a microscope, and you stain so that you can see how the cellulose fibers are aligned, which is completely not random and very, very intentional. I think it is. That is, I guess, the time when I decided that I should completely.
Dude, this is cool.
Change what I'm doing.
Okay, so if we're going to be talking about sustainable polymers, inevitably people are going to want to boil that down to a single number, and that number is CO2. And it's more than that. Tell me, what else should we be considering to capture the big picture?
Yes. Now, this is a really great common misconception, or people are so obsessed about carbon footprint, which is important, absolutely.
No doubt.
But it's not it's not the only thing that we should be looking at, because that is associated with, it should be associated with everything that, all the processes that we need from the time that we drill oil or that we use whatever corn feedstock or whatever resource, we have. We break it down, we refine it, we have the monomer that we need, we polymerize, we formulate, because the plastic that we use actually is not a plastic, it's a formulation.
That's right.
All of those have different, come from different processing lines.
Plasticizers, whatever else.
Exactly. Yeah. And then there is an end-of-life component as well that could be, of course, recycling, an ideal case scenario, but there's also, but in reality, at least in the US, we are landfilling everything, right? So there is also the end-of-life effects that are associated with our incubation of our products in a landfill, leaching to the environment, ecotoxicity, and all of those other things that a life cycle assessment gives you. That is not just the carbon footprint.
So what's needed to make that happen? Like, there's people that do life cycle analysis, and I'm sure they talk about that sort of stuff. Is it the fact that we as material scientists are just ignorant to these other considerations? And so even though people are studying them, we're too focused on not the wrong thing, but there's more to it than what we're paying attention to?
I don't know to what extent it should be the responsibility of just the people that develop. Like, it is true that we have built for so long walls in between us, which are now actually, we're at a time that every faculty member that I know is claiming or actually doing interdisciplinary work, right? Like, you're doing interdisciplinary work.
Yeah, absolutely.
I'm not a biologist. I'm a physicist. So, by the way, so if I said anything wrong about the biology part, I'm excused. I have never taken a single biology class after I graduated high school. So it is true that traditionally we were not talking to each other, but now we are. And it's just so difficult when you are using that methodology, which is great, very nicely developed. It has 1,000 different things that you have to account for, including, for example, my students go and take annually, we go and do an annual harvest in the nearby shore.
This is so
that
cool.
We can fish the seaweeds that you smelled in our lab. So they are there.
Can verify it was seaweed.
Exactly. So this is locally grown and harvested from the shores of Washington, so local. We let it sun dry or whatnot if we want to be super sustainable, right? If we don't care, we put it in the freeze dryer.
Or freeze dryer,
Yes. So because we don't starts changing things. So that's why we want to be very careful about that. But then let's say that we have that feedstock that we bring in the lab. Even the choice of the container in the freezer, will it be a plastic bag or will it be like a paper bag that we store it? Even that gets recorded into the LCA calculation. So the problem, in my opinion, is yes, we're not traditionally trained. Like, I teach material processing. Now I have a module for LCA so that students can learn, do design, even from primary, just a little hint for them, and they can study further if they want. So I guess the other part of the problem is the lack of transparency in the values that we use for everything. So, for example, my student is trying to do the LCAs for our bioplastics. We use the hot press, we have our own freezer, our own freeze dryer, and whatnot. So she goes in literature. I told her, go find at least 5 papers that use different ovens and different freeze dryers and all of those, get an energy consumption value from those. Then she got a little tool that measures the energy consumption right there in our own outlets.
Way cool.
It was 5 times higher, obviously. Then if you look at other papers, you cannot, it's very, very difficult that you will find values for every single step. And because if you really want to compare, as we wanted, with other types of plastics, synthetic or bioplastics, it is very difficult because there's also, if it's a company product, you're going to find the value. You're not ever going to find the granularity so that you can go and compare and see all of those values that went in this calculation. So it's very difficult for us to compare between our labs because we don't use the same values. We don't even, for me, it is easy if we can publish. Let's say we publish a paper and then we have the data available over there. Sure. But I'm not a company, right?
Yeah.
So I don't care if we put the data there.
I saw a similar problem in the battery field. I saw people will cite, different batteries or X amount of CO2 emissions or whatever else, right? And somebody did a meta study, right? A study of the studies, and showed that the variability, and that's just in EV batteries, is wild, like totally crazy. Huge, like the variation was, I'd have to pull the numbers, but it's hundreds % like difference, which tells you that we just don't know. Anybody who's saying like making policy decisions or things on these just needs to, I'm not saying they shouldn't do it, but they should be aware that it's happening in the context of a lot of uncertainty.
Exactly.
And I'm guessing it sounds like it's the same for
bioplastics.
Same.
Even as you were working in the lab and you saw our biodegradation chamber, right?
Yeah.
We were talking about the difficulties in reproducing those results, because if you put your materials in soil and then you record, even if you measure the evolved CO2 as we do, following an ASTM.
Yeah, we talked about this. Like your dirt that you used here, if I was in Boston, for example, or in Salt Lake City, and you said, hey, reproduce it for me, I couldn't reproduce it because I would go out and get some dirt, right? From, even if you tried to describe, like get it from under a tree or whatever you want to describe it, right? Or from a compost provider.
Even if you have the same,
it's going to be different. Right? There's variability. There's serious variability on the bacterial cultures that might be there. Yeah, even controlling for composition, right? The bacterial variability is going to be significant.
It's a very, very big problem. I know that people are trying to develop even more refined, standardized, even though we do have ASTMs and ISOs. I know that people are pushing for more refined versions of those and more reproducible, but it's really a big challenge. And actually another big challenge, if we think about like in terms of society and what they think about what we do, because you always want to have an impact, right? There is so much misinformation.
Yeah.
What is about, there is no, so I'm a member of the AUPAC subcommittee on terminology, I guess. So, we sit and debate for hours of how you should call a cis and trans bonded, whatever. For the polymer action division. Okay. So just for polymers, not for inorganics. But there is not a mandate, but like we launch one of every now and then we publish, I guess, instructions of how you should call things. So there is a very specific explicit instruction to not use the term bioplastic because there is no, it's not defined, and people just take it to mean whatever they like. Even biodegradable, people use it incorrectly. And we had a visitor a couple of months ago. The U.S. State Department organized an exchange of some experts between the U.S. and France. So I got 5 or 6 people, activists and like policymakers from France that visited our lab. They are, of course, active in the area of plastic pollution. So we had many discussions about how the US and how Europe, but specifically France, regulates polymers differently. And we were discussing with a person that is in the city of Paris for their sustainability office.
Oh, cool.
And we were discussing that I think they already implemented, if I'm not mistaken, they completely forbid all companies to use the term biodegradable until there is a definition that we can all agree on. If or not, I don't know if it's already or she told me that it will be, I guess, a law soon. But I think this just shows you the misinformation, and it's a very sensitive topic. So that's why I want always, even with reviews like that or even public talks, we really have to be very careful. Define.
Yeah. One thing I noticed in this article is you do a really good job of these little side things of right here, bioplastics. Here's how you describe it right here. Polymer derived from biomass that at some stage in its processing can be shaped by flow. Like, I think it's really great that you're defining these terms. So it's really, first off, it's a review. So that's great. For somebody who doesn't know this field, to be able to like understand what's going on was really helpful. But I think it's important because it matters in how we describe and use these materials, that we're all talking about the same thing.
Yeah, exactly. For it to be a plastic comes from thermoplastic, which is a subcategory of polymers that are shaped by heat and flow.
That's right.
And multiple times, right? It's not a thermoset. It's not your epoxy that you only one time you can form. So the fact that I can regrind and reprocess this, that makes it a plastic. The fact that it has components from biomass, in our case, all of it is biomass, you can call it then a bioplastic. But I think bioplastic is not even the worst of it, if I'm mistaken. Like, okay, people can call PLA and thermoplastic stars and PHAs. It's not a problem that they call them bioplastics. The problem is that the end of life. Yeah. What is biodegradable? Biodegradable is...
And under what conditions? So I was just going to say, we have a great review article on marine biodegradable plastics. I'll put in the show notes for this, because to that point, we basically show like, it's not very fast. And yet will it eventually biodegrade? Yes. But if it takes 20 years, shouldn't that change how you would react to it as a consumer? Would you really buy it and chuck it if you knew that it was going to take 20 years versus a year or something? Like, yeah, of course it would.
Like if we buy a bag of our coffee that says compostable bag, like this one here.
Okay.
But you see that it says now it is obliged to write on that, do not put it in the backyard. I don't know how it's commercially compostable only.
Yeah. May not exist. Commercially compostable area facilities may not exist in your area. So that's them saying like you
should not put it in your backyard. It will never. So this is PLA actually. It will never. Or it will take, I don't know, hundreds of years, right? But there is infrastructure for its compostable. If you live in Minnesota, for example, of course you can absolutely use your composting bin, and it will go to the right place, and you will have it processed as needed. But I don't know if you have that in Utah, for example.
I don't think so. It's a big empty state. I think they're going to put it in the dirt.
Yeah. Well, I think as long as we find words that are clearly communicating the do not eat or do not put it in your in ocean, or I think this needs to be somehow clear and also globally clear. Not just, it's very sad and worrisome that we have different regulations in the EU versus USA versus Canada, even Canada and USA. I mean, come on, they have different regulations for end of life and for terminologies. So it's a big problem.
Yeah.
Arguably, no, it's not as big as the actual problem, but it is big because it does command consumer behavior.
Yeah.
It influences consumer behavior.
100%.
And it shouldn't be, I don't know, it shouldn't be left to the consumer to do research to understand what every one of those options mean. I mean, come on.
Yeah.
It definitely should not be with the consumer. Consumers should just be clearly informed about the impact of possible impact of their decisions.
Yeah.
But we should not expect them to be college professors.
Right. So what else do you want people to know? Before we go, any last things that you'd like people to understand about this field in general or the future directions or anything like that?
I think what I would like people to know is that there's a lot of activity in this area, and it's not, it does have high risk and like more conservative approaches as well. There's a variety of solutions to this very important problem that we have created. It's not something that will, I don't think that all solutions will be fruitful or be applied, but also I think we are close with other types of, with the innovations that are happening right now. I don't think it's going to be 20 years before we have different types of plastics for us to choose from. I think we're much, much closer. So, and people should maybe, I don't know how you can expect people to not jump to conclusions too easily. But for example, like if you say that this was made by bioengineered organisms, people get goosebumps. It's like, oh my God, it's bioengineered organisms. But I mean, you really have to understand what they were made for. If you just have a genetically modified species that creates a drug that is useful for you, or a polymer that can really decompose afterwards very easily, I guess you shouldn't focus on the bioengineered part as if this is like some kind of a demon. I don't know.
Yeah. Completely agree. Well, Eleftheria, thank you so much. Super, super cool episode. I've really enjoyed, first off, the visit to Seattle is amazing. And it's been wonderful hospitality. You guys have an amazing department here. So excited to get to know it more. And this has been a great episode. I'm just going to close by reminding our listeners that this episode is sponsored by Materials Today, which is an awesome journal, by Elsevier, which is an awesome company in the publishing space. We're grateful for them providing awesome resources like that journal and doing more. They actually have a whole community around material science. You can check them out, materialstoday.com, elsevier.com. We appreciate them. And obviously, we are grateful for the other people that make the show possible. Our team, Andrew, Jared, and I, the people that make the music, Alphabot, Kolobyte, super grateful to them. If you have feedback for us, we would love to hear it. We're going on our 6th year now, which is completely bonkers to me, and we wouldn't be doing it if there weren't people out there listening. So if you've got a favorite episode that you like and you want to tell us about it, it's great. If you want to hear an episode on some topic, tell us and we'll come make it, right? We honestly, almost all the episodes we're doing now are fan requests at this point. So you can find us really easy. We're on Instagram at the at materialism.podcast. You can send us an email, our Gmail, materialism.podcast@gmail is the way to go, or on Twitter or whatever else. Anyways, it's been a great episode, and we'll see you guys next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world and are bound only by their imaginations in manipulating those materials.